screen?
Yes, thank you.
Okay. So as Luigi mentioned, so I'm going to talk about the kinds of, so first of all, our approach for treating large systems in Big DFT, and give you a few examples of the kind of things that we are able to do, particularly thinking about the example of simulating OLEDs. So I guess this is a problem with which most people are familiar, but the idea is that we want to be able to design new materials using computational approaches. And probably most people are familiar with the motivations behind being interested in organic electronics, so they have a number of nice properties. And really what we'd like to be able to do is some kind of process like this. So propose some new molecule, calculate some properties, identify whether it could be good for a particular application, and then ultimately be able to develop new technologies and more efficient devices. So there are some challenges associated with this, and one challenge in particular which we're interested in the case of OLEDs is that they tend to be very disordered systems. So if you would take an example like this, which is a classic host-gas system, one of the things you might be interested in calculating to understand how well this material will work in a device would be charge transport properties like transfer integrals. And the typical approach is to take some cluster or realistic morphology and to extract pairs of molecules and then calculate transfer integrals for these pairs. But actually, one of the things that we know is that the environment surrounding this pair of molecules can have quite a big difference on the parameters that you calculate. And a more realistic approach would be to do something like this. But of course, if you're going to be able to calculate properties in systems like this, you need to be able to treat large systems from first principles. And so this is one of our main areas of interest in the Big DFT code. So Big DFT's main interesting feature is that it uses a wavelet basis set, which is a basis set with which most people are probably not so familiar. So it has wavelets have nice properties for use as a basis set for DFT. So they're localized in real and Fourier space. They have multi-resolution properties. So if you would consider the simplest family of wavelets, you have two different types of functions. So the scaling functions and the wavelets. And by combining these wavelets and scaling functions, you can have different levels of resolution, which allows for a multi-resolution adaptive approach. It's also a systematic basis set, so you don't have problems of overcompleteness. You can push to the complete basis set limit, and the kinetic energy, for example, can be written as an analytic form. So the wavelets that we use in Big DFT look like this. So they're called the least asymmetric Dobrasheys of all the 16. So they're orthogonal, they're compact support, so exactly 0 outside this area, and they can exactly represent 8th order polynomials. And so if you would use this basis set in a DFT code, like we do with Big DFT, you end up with this multi-resolution property, as I said. So we choose to have 2 levels of resolution. So our example grid looks something like this. We have a fixed grid spacing throughout, and then we have what we call a fine region close to the atoms where you need more degrees of freedom, and a coarse region further away where you have fewer degrees of freedom. And this leads to a very efficient approach, which is particularly suited for inhomogeneous systems. So a lot of what I'll be talking about in this talk is more oriented towards molecules and molecular systems, but we can also treat periodic systems. So we have explicit free wire surface and periodic boundary conditions. We have an analytic pseudopotential approach, and we have a massively parallel implementation, so we get quite efficient performance up to a large number of nodes. So this is, for example, 500 atoms of bulk silicon, and we can do a single point calculation of the order of minutes if we have enough nodes. And similarly, we have a GPU implementation, which is particularly useful if you're looking at hybrid functional calculations, where we get excellent speeds up with our GPU implementation. We've also more recently been working on a Python interface to Big DFT called PyBigDFT, which allows for kind of efficient pre- and post-processing of results, which means we can go towards a workflow approach. And as I think we've already mentioned, BigDFT is open source, so freely available. So as Luigi already mentioned, the original BigDFT implementation was oriented towards a cubic scaling approach. So because of the nice properties of wavelets and the efficient parallelization, we can treat up to the order of 1,000 atoms, maybe a bit more depending on the system. But at some point we run into this cubic scaling limit, which is common to most DFT codes, which is the same for both time and memory. Eventually we hit the point where we can't treat big enough systems for the types of problems that we're interested in. But we do know, and as has been known for quite a while, that the behavior of large systems is short-ranged or nearsighted, and more specifically, the density matrix decays exponentially in systems with a gap. And so we can exploit this approach to treat large systems. So as has been done in a couple of other codes, so OneTEP, for example, that some of you may have heard of, we redefine our extended cone sham orbitals in terms of a linear combination of localized support functions. So these support functions have some small user-defined radius. They're atom-centered, and we have a minimal number, so usually one support function per hydrogen, 4 per carbon, nitrogen, oxygen. And these are numerical functions which we expand in Wavelet, so we end up with 2 levels of basis set. And they are numerical functions, but they usually have some resemblance to S or P or D-like functions. They're usually quasi-orthogonal when we work at the gamma point only, because we're interested in big enough systems. And this means the support functions can be real. So once we've defined the support functions, we can also write the density matrix in terms of the support functions and this density kernel. And once we have these 2 key ingredients, we can write the Hamiltonian, the overlap matrix, and use these to define the total energy of the system or the number of electrons. So our support functions, as I said, are represented on a wavelet grid. So we still have these 2 levels of resolution, but then we have some spherical regions on top. So as I mentioned, this is a minimal basis. If anyone is kind of familiar with Gaussian type approaches, you might wonder how we can be accurate using a minimal basis. So there's an extra step. So we have the extended cone sham orbitals, which is a cubic scaling approach, which is very accurate. We can go to some kind of localized minimal basis set approach, which is going to be potentially a linear scaling approach, but low accuracy. So the final step is to optimize the support functions for the system. And again, this is a similar approach to use in the OneTEP code, but it means we're able to have a minimal localized basis, which is somehow adapted to the system. So you can see that support functions on a carbon atom might look slightly different depending on the local environment of that carbon atom. So our overall algorithm has 2 kind of steps. So one where we're optimizing the support functions, then we optimize this density kernel, and then we kind of repeat until both of these things are converged. We have a few different methods for optimizing the density kernel. So the Fermi operator expansion method allows us to be linear scaling, but we also have a direct minimization approach, which means we can have a basis set which is able to include some virtual states, which if you don't use this approach, usually the support functions are oriented towards the ground state only. We can also easily calculate forces, so we can do geometry optimizations and molecular dynamics. And usually we don't have access to the cone sham energies directly in the calculation if we use Fermi operator expansion, but we can also just do a one-shot diagonalization at the end. So once we combine these support function and density kernel optimization, we then end up with strict localization. So strict localization means we end up with sparse matrices, and we can take advantage of this sparsity to have a linear scaling method. So the level of sparsity will depend on the type of system, so the size and the dimensionality. So for example, if we would take a graphene nanoribbon versus graphene, you can see that the nanoribbon has a more sparse density matrix at the same system size compared to the graphene. And so this means that for the nanoribbon, the linear scaling approach has a much lower crossover compared to the cubic scaling approach than it does in the graphene case. So usually this crossover is somewhere of the order of a few hundred up to about 1,000 atoms. But you can see that the approach is nice and linear scaling. So here I'm only showing up to about 3,000 atoms, but we can treat it to the order of tens of thousands of atoms, and usually are working at kind of the several thousand to 10,000 atom regime. So once we've defined our linear scaling approach, we can also go a bit further for certain types of systems. So the majority of our computing time, which affects this prefactor, so the point where the crossover occurs, depends on doing the support function optimization process. But we know that these support functions are kind of dependent on their local chemical environment. And in a lot of systems, we have many atoms which have the same chemical environment. So if you would visualize the support functions for a water droplet, for example, you can see, at least just at looking at them, they look pretty similar between water molecules. So then the question is, can we somehow take advantage of this similarity between chemical environments? So the answer is yes. There's one slight complication that of course, in a water droplet, for example, we have molecules with different orientations and positions. So we've implemented a scheme which can detect rototranslations between some reference coordinate and then apply an accurate and efficient interpolation scheme to convert support functions in one orientation to support functions in another orientation. And if we put these things together, we can define what we call a fragment approach. So in this case, we start with some small template molecule. In this case, it would just be one water molecule. We optimize the support functions and do a full linear scaling calculation, which is of course very cheap because it's a very small system. And then we replicate these support functions and use them as a fixed basis for the full system. So this completely cuts out the support function optimization leap for the large system. And in most cases, it results in a decrease in computational cost by up to an order of magnitude. So how well does this approximation work? Well, it depends very much on the system. If we would consider a water dimer, we can see that as the water molecules approach each other, we start to get very large errors compared to fully optimizing the basis, because we've assumed that the molecule should be infinitely separate and gas phase-like. But of course, as we go to larger distances, this approximation is better and better. So it depends how closely interacting your molecules are as to how well this approximation works. Similarly, we're assuming that we start with a rigid water molecule and we just rototranslate the support functions. But of course, in a realistic water droplet, there's going to be some distortions occurring in those water molecules as they're vibrating, for example. And so this also has some accuracy, some effect on the accuracy of the approach, but our rototranslation interpolation scheme is able to handle these distortions. And we have defined a cost function, J, which allows us to determine whether there's too much noise in the system to be able to use the approach, or whether the noise is small enough to be able to use the fragment approach. This fragment approach is also quite a convenient scheme within which to use constrained DFT. So for those of you who are not familiar, the idea of constrained DFT is to find the lowest energy state which satisfies a given constraint on the density, usually a charge constraint. And in general, we want to associate a charge with a particular fragment of the system. So we can easily do this just by adding an extra constraint term to the Cohn-Sham functional. And if we use a Loudon-like approach, we can associate a given fragment with the weight function. So how well does this work? Of course, depends on how well the fragment approach works. So if we have too much distortion or too closely interacting fragments, maybe it's not appropriate. But in general, this approach works quite well for the types of systems that we're interested in. I'm not going to talk particularly about extended systems in this approach, but just as an aside, we can also adapt this molecular fragment approach to extended systems by optimizing the support functions in embedded pseudo-fragments. So we've shown that this works quite well for nanotubes or for extended systems like graphene with the defects. And just to show the savings that we can make when this fragment approach is appropriate, going back to the graphene example from earlier, you can see that previously the crossover with the cubic scaling approach was at around 1,000 atoms, but we save a significant amount of wall time by using the pseudo-fragment approach, and our crossover is significantly decreased, only of the order of a couple of hundred atoms. So we are able to treat both molecular and extended systems, providing there's some degree of repetition using this fragment approach. Otherwise, we use the full linear scaling approach. Then there's also some questions about what we do, what can we do with the ability to treat thousands of atoms. So if we would do the kind of semi-quantitative schematic looking at different methods for electronic structure, we have on the one hand our highly accurate quantum chemistry methods. On the other end, the length scale, we start to have our classical methods, which are able to treat the very large systems. And one of the nice things about linear scaling DFT is that we're able to bridge the gap between these two extremes. which means we can, on the one hand, have a fully quantum mechanical approach. On the other hand, we can treat large enough systems that we're able to directly validate classical approaches at scale. But then the question arises, just because we can do lots of atoms, how do we know whether it's strictly necessary to treat so many atoms using quantum mechanical approach? So one of the other things that we've been working on is a way of reducing the complexity of large-scale DFT calculations. So we often in DFT want to extract local quantities, whether that's doing some kind of projected density of states or looking at atomic charges or multipoles. And the advantages of looking at localized quantities is that we can connect with classical methods, so for example, electrostatic embedding approaches. So the nice thing about the linear scaling DFT formalism is that we can use the locality of the support functions to map to localized degrees of freedom. And this enables us, in some sense, to reduce the complexity of the problem. So we've defined some indicators which allow us to quantify and analyze large systems. So one of these is the purity indicator, where we use information coming from the density matrix to identify fragments of the system which can be treated separately. So this is in the sense of the fragment approach, but more in the sense of understanding whether or not a fragment approach would be appropriate. Then we also have the fragment bond order method, which allows us to quantify interactions between these fragments. But the possibility of doing both these things is strongly dependent on the basis, and this ability to reduce the complexity really relies on having a localized minimal basis, which is where the support functions come in. So just to give some examples of what this looks like in practice. So if we would take DNA, a large system of DNA in some solution, so about 15,000 atoms in total, we can run a complete linear scaling calculation in a couple of hours. Actually, this calculation is quite old. We can actually do system sizes of this size in sort of the order of minutes rather than hours if we have enough cores. But once we've done our single point calculation, we can use this purity indicator to identify unbiased separable fragments. And this allows things to do things like analyze the charges of fragments so that we can see that the nucleotides are identified as separable fragments by this purity indicator measure. And so we can analyze what are the charges on different nucleotides in the system in a way which doesn't require you to have any detailed knowledge of the system in advance, but purely coming out of the quantum mechanical calculation. So in a similar way, we can look at, this is a lacase enzyme, that using both this purity indicator and the fragment bond order, if we know that certain atoms feature in our active region, we can use the fragment analysis to identify how big this active region needs to be, and also how big an embedding region needs to be in order to be able to reproduce, for example, the density of states of the full system using just this active and embedding region. We can also have some kind of coarse-grained graph-like view of the system. And again, this information doesn't require us to know anything ahead of time, particularly about the system, but we can obtain these sorts of maps of the system just coming from the results of a linear scaling calculation. So how do we put all these things together to be able to look at OLEDs? So one of the examples we looked at a few years ago now was this host-guest OLED system, which I mentioned already. So this is a CBP, a classic host molecule doped with 8% of this iridium ppy3 classic guest molecule. So we have some kind of large realistic disordered morphology. And what we were interested in is understanding how the charge transport parameters are affected by this environment. So partly using constrained DFT to understand the polarization effects. So just to show how well the fragment approach works for this system, you can see that just like with the graphene example, we get significant savings in computational time by using the fragment approach. So around about 7 times cheaper than linear scaling, which means we can do several thousands of atoms in the order of 15 minutes, as I mentioned. And at the same time, we're able to reproduce the density of states using this fragment approach. It agrees very well with both the cubic and the linear scaling approaches. And our error in energy is of the order of 30 millieV per atom compared to the full cubic scaling approach. So it works really quite well for these systems. One thing we do find is that if we want to calculate electron and hole transport parameters, then we need to make sure we include an extra cone-sham state in the support function optimization so that we can represent the LUMO in the basis. And this is something that we can do using the direct minimization approach that I mentioned earlier. So using this fragment approach, we calculate both transfer integrals and on-site energy. So the transfer integrals are calculated using a fragment orbital-like approach. So we start by generating a support function basis for isolated host and gas molecules, and then in a neutral cluster, we calculate both these transfer integrals and the on-site energies where we're using constrained DFT to confine a charge to the molecule of interest, and then calculate the on-site energy as a difference between the two. And what we find is that the transfer integrals, we can really see quite a lot of dispersion due to the disorder in the system. Although as it happens, at least at the level of the fragment orbital approach, you don't really so much see the effects of the environment. But when it comes to the on-site energies, we do see not only some significant dispersion in the values, but we also see a net shift in average value compared to what you would get if you would just look at an isolated molecule. So in this case, it really does make a significant difference being able to treat some kind of realistic morphology rather than just looking at gas phase molecules. So we want to take this one step further. So we're more recently been looking at OLED molecules which are based on this thermally activated delayed fluorescence approach. So the idea is that we want to go away from emitters like I showed in the previous slide, which are based on iridium, other common examples being based on platinum, because this is expensive and unsustainable. So the advantage of TADF is that it can be both efficient and have purely organic emitters, so like this classic example of 2CZPM. Of course, we also have the problem, like I showed in the previous slide, that the structures are very disordered and we can't look just at molecules in isolation. We also have the problem that these molecules have rotational degrees of freedom, so there's some conformational disorder to also take into account. So the first stage, we're looking at the ground state electronic structure, so using this complexity reduction approach that I showed previously for the biological applications. And also at the same time, we want to combine this DFT calculations with X-ray photoelectron spectroscopy. And in this case, I've also been looking at calculating the core spectra using MADNESS, which is another wavelet-based DFT code. But more interestingly for TADF, we want to go beyond the ground state. So TADF relies on this mechanism of reverse intersystem crossing between the triplet and singlet energies. And this is really only possible in systems where we have a small singlet triplet splitting. So if we want to do any kind of computational design approach, or even just understanding whether a particular molecule could be appropriate for TADF, we need some way of calculating singlet and triplet energies. And we also have the complication that this singlet triplet splitting could be strongly influenced by the environment. And in TADF molecules, there's often a mix between charge transfer and localized excitation. So we need a formalism that can treat both of these types of excitations. So the typical approach is to use TDDFT. One of the problems is this becomes very expensive if you would start to treat large systems, or even with not so large systems. And it also has problems with long-range charge transfer states, which can sometimes be fixed by using range-separated functionals, but this also becomes very expensive and isn't practical for the system sizes that we're interested in. So really, we need a new approach that can calculate these singlet and triplet energies, but which is designed for large systems. So I've already talked a bit about constrained DFT. So in the classic formalism, it's designed for treating charge transfer states. So the advantage is that it's computationally cheap, which means we can treat large systems, and also, as I've mentioned, works well with our fragment approach. And the fact that it can treat long-range charge transfer excitations is a promising advantage over TDDFT, which has problems for these types of states. And if we also just look even kind of qualitatively for this classic zinc bacteriochlorine charge transfer complex, you can see that at least qualitatively, CDFT gives us something quite similar to many-body perturbation theory. But then the question is, what do we do about locally excited states? So we've been working on defining a different type of constraint, which instead of having some kind of a spatially based constraint where we're transferring charge between two different regions. We want to just have a local constraint where we're imposing a constraint between orbitals. So in this case, exciting an electron from the HOMO to the LUMO. And if we could define this constraint, then we're able to treat also local excitations with all the same advantages of spatial CDFT, namely that we can treat large systems. So we've been, at the moment, implementing a workflow for benchmarking constrained DFT compared to both TD-DFT and the delta SCF approach, which is another possibility for treating excitations that's relatively widely used. So we've been benchmarking Big DFT also against the NWChem code, looking at a relatively well-used basis set for excitations. So at the moment, we're always assuming a pure transition. So for, like I've shown the schematic, that we're exciting an electron just from the HOMO to the LUMO. But in principle, we could also treat some combination of excitations that might include components from the HOMO to -2 to the LUMO, etc. So looking at this, for example, of a naphthalene molecule, you can already see that comparing delta SCF, TD-DFT, and our constrained DFT results, it's very sensitive to the method we use, but also, even at the level of the same method, very sensitive to the functional. And also the basis set. So here I'm showing that the width of this line basically means that there's some deviation between our Big DFT results and the NWChem basis set. But what you can see is that the constrained DFT gives us results which are in line with, relatively in line with TD-DFT. And particularly for constrained DFT, we're only using PBE, so a semi-local functional, but the results agree relatively well with what you would get using a hybrid functional. We've also looked at other A-scenes, and the behavior is quite consistent across the different A-scenes. And in this case, it is a local excitation, and we expect the excitation to be more or less pure, so it falls under the well-behaved case. We've also been looking at how this approach works for TADF molecules, where the calculations are currently in progress. But the nice thing is that this formalism works well in combination with the linear scaling Big DFT. So our aim, once we finish benchmarking gas-phase calculations, is to already be able to look at excited states in some large morphology. So just to summarize what I've talked about, and then we can maybe discuss some of the details a bit more. So the Big DFT code allows us to have a range of methods that aim from the cubic scaling treatment of large systems, all the way, of small systems rather, all the way up to large systems. And at each stage, we can make a single additional approximation, so including like some kind of localization, and taking advantage of repetition and fixing the basis. So that each stage we're being systematic and controllable, and this means we can validate the additional approximations that we're making, whilst being able to treat large systems. So we can also introduce various indicators that enable to quantify things like active and environment regions, or define the suitability of using the fragment approach, for example. And this makes Big DFT very useful for being able to test and compare new methods which are aimed at large systems, while always being able to benchmark with respect to methods which are designed for high accuracy at small systems. So this means we can also treat, particularly thinking about OLEDs, realistic disordered morphologies, and understand the importance of environmental and statistical effects. And we're currently expanding this for looking at excited states. As I mentioned, we have this Big DFT approach, so we've been working at increasing the user friendliness, particularly for people who aren't necessarily interested in all of the gory details that go on behind the scenes in linear scaling Big DFT. So we've looked at simplifying and automating a lot of this analysis. As I said, at the moment, we've been benchmarking CDFT and gas-phase molecules, but we're planning to do calculations in environments very soon. And of course, one of the ongoing challenges is adding new functionalities into Big DFT. And so just to end with the acknowledgements, so I'm funded by EPSRC, also use computing time on Archer, and this work on OLEDs, particularly Luigi and Martina Stello, who's a postdoc in my group that's also on this call, and Chris Antap is a PhD student who's also been working on the OLEDs. So happy to open up to discussion.
Thank you very much, Laura, for the your recent work. So the floor is open for questions.
Hi, this is Sergey. So you mentioned you have periodic implementation. You can treat metals, have K points, or is it just periodic boundary conditions?
So we can treat metals, but we don't have. So we have K points for cubic scaling Big DFT, but not for linear scaling Big DFT. So it's assumed that if you want to treat large systems where you need K points, then you would use the cubic scaling approach. If you want to treat very large systems, either metallic or semiconducting, then it's assumed that you're a large enough system size that you don't need K points.
Oh, that makes sense, actually. Yes, that makes sense.
Also, I may add that surprisingly enough, we have been able to make working the algorithm for linear scaling approach, which is generally conceived for systems that have a gap, with systems that are metallic but with a finite electronic temperature. So there has been one paper in which we have shown that if one would like to treat defects in large supercells where the size is reasonably large, not to have to deal with K-point sampling, and also because of the concentration of the defect, it is indeed possible, although challenging, to make the electronic structure to converge within a linear scaling computational wall time. So it is even possible to combine this approach with the solid state fragment method that Laura mentioned. So although these studies, as I have said, are more exploratory and based on a feasibility principle, it is reasonable enough to expect that when there is a finite temperature, the density matrix still have a localized behavior, and this means that the linear scaling is conceptually possible. We have been able to prove that by explicit calculations, whereas for traditional metallic systems that have periodic supercells, the most convenient approach is by far the traditional cubic scaling approach with K points, which indeed is present in Big DFT code since let's say the first releases, and that is the present situation about periodicity in wavelets.
And another question, maybe I cannot say I catched everything that you're saying. There's a lot of information. So maybe you mentioned this and I missed this. During this support function optimization, so if you have relaxations, then you need to repeat this every time that you do relaxation, or there is some optimization that takes that into account, and you don't need to re-optimize after every change of atomic configuration.
So usually we do re-optimize when we relax a structure, but we use the support functions from the previous geometry as a starting guess. So what you find is that actually it becomes much quicker because you don't need to do so many optimization steps for the support functions, because usually the geometry is not changing so much.
But would it make sense, say, to run molecular dynamics with this approach?
I mean, yes, we have run molecular dynamics with linear scaling Big DFT, and what you do find is that you do usually need to re-optimize the support functions, maybe not every but generally the support function re-optimization is quite quick because the structure doesn't move so far at each time step.
What is interesting to be considered in this context is always the computational wall time. Linear scaling doesn't mean faster than force fields, of course. It is always much more costly than a force field approach. But the advantage of linear scaling is that you can convert the computational wall time into a per atom quantity. So you know in advance, if you simulate a small system, you know in advance the wall time you are going to need with a given computational power to simulate a larger one. So I can give you some rules of thumb for systems which have a net gap and for which a linear scaling approach is very appropriate, like, for example, biological systems or systems in general with organic molecules. The performance is often measured in our group in terms of CPU minutes per atom. So the cost of a single point optimization at the beginning of the molecular dynamics, which, as Laura said, would have been the most costly one, is in general, depending on the architectures you are going to run the simulation, is in general ranging between 5 until 15 CPU minutes per atom. So that would give you, if you do the math, would give you numbers like the one which Laura showed. If you have a few hundred cores, you have to wait a few dozens of minutes for having a CPU time, for having a calculation of a single point approach. This, of course, is orders of magnitude larger than the time you're going to need for force fields approaches. Even though it is a state-of-the-art time for DFT, it is difficult to believe that one would go to large-scale systems. It would be still possible to preserve the same paradigms that are employed for first-principle molecular dynamics simulation with smaller ones.
Right. I'm not hoping to have something comparable to force fields. Now, what you just described, so this is wall time or this is CPU time, and how does it scale with CPUs?
The wall time, you can get the wall time by multiplying the CPU minutes per atom times the number of atoms of your system and dividing it by the number of CPU cores you
So it scales with
in
cores perfectly, basically.
In a reasonable range, the scale at the first approximation, if you want to give an orders of magnitude of your calculation, can be assumed to be perfect, because when one has up to few support functions per CPU cores, there are enough data to be to make the parallelization efficient.
Mm-hmm.
We have in general efficiency that range between 95% and 75% in most of the cases, except pathological situations that may be associated due to some load unbalancing problems. If one provides a repartition of number of cores that is not necessarily in agreement with the way in which the localization radii are distributed. But these are rules of thumb that can give a faithful representation of what could be the expected wall time. There are always exceptions that can be dependent also on the electronic structure of the system. The numbers I just said assume that the number of outer loop iteration is of the order 10 to 15, which is often the case if the system is well behaved, but if you have some metals or some spin or some charge transfer during the optimization, things can somehow impact. The advantage is that this is system dependent. So if you simulate that for a small system that have a similar electronic structure of the large one, you can get a realistic estimation of what you could get in terms of wall time.
Thanks.
Can you comment on the difference in efficiency between the wavelet basis set and the basis set used in the one-tap code?
Yeah, so efficiency, so as in comparing like the wavelets versus the p-sync basis, or
Yes.
the overall approach.
Yeah, so I have some experience with one-tap, but from what I've seen, the crossover so the superiority of the linear scaling code compared to cubic scaling, like castep, occurs at much higher system sizes than what you say happens with Big DFT. Is it because the wavelet formulation is more efficient than sync, or would you say it's broadly comparable?
So I think that is part of it. Another large part of it is that so a lot of the results I've shown here are in free boundary conditions or surface boundary conditions, and in one-tap you're by default in periodic boundary conditions, and perhaps making some approximations thereafter to simulate open boundary conditions. But what you can see already is for Big DFT, having something that's quasi one-dimensional versus having something that's two-dimensional already makes a big difference for the crossover. If you would go to something that's fully periodic, the crossover is going to get even higher again, particularly if it's a difficult system for linear scaling DFT. So even bulk silicon, for example, which is very friendly for cubic scaling, DFT is not so well behaved for linear scaling, and the crossover might be much further towards 2000 atoms, for example. So I think that does play a role, but also the way we do the support function optimization. So I didn't talk about it, but we introduce a confining potential which helps keep the support functions localized within their radii, and this helps things. Things are generally better conditioned in the wavelet basis set than they are in the p-sync basis set. So this also makes a difference.
Thanks.
I may even add that the point which we are experiencing, it is now few years that we are able to deal with systems with many thousand atoms. What it is definitely happening is that when you realize that you can simulate systems of larger size than before, you immediately realize that also the way in which the DFT calculation has to be set up and interpreted and exploited for production is substantially different from the computational approach and the investigation paradigm you would get for few dozen atoms up to few hundreds. So even though the calculations have a crossover point which is interesting, and even though the calculations still stay at the linear scaling, we can't do less than that. The way in which the calculation have to be treated, due to the fact that they are undeniable heavier than effective approaches that don't employ quantum mechanical consideration, such kind of consideration somehow are transposed into the computational paradigm and the investigation which is done. You treat linear scaling calculation differently than cubic scaling calculation. The advantage is that the approach provides you localized information that enable you to simplify the complexity of your calculation and to understand quantities onto your system that are difficult and challenging to be understood, if not impossible, with the traditional cubic scaling approaches. So this is a consideration that, in my opinion, is interesting to bear in mind when one wants to approach calculations of large-scale systems in DFT.